One of the big novelties of the 1687 standards is the native support of functional access to registers thanks to the PDL language. Functions can be defined in PDL and then need to be retargeted into a pattern set. Even though this operation is conceptually simple for simple cases, it can become extremely complex computationally wise when we will have tens of hundreds of registers on which we will need to retarget concurrent PDL. To explore this situation, we set up a series of use cases exploiting our MAST tool. The idea is to take just a simple PDL code that makes a series of random value writes to a register, and then to retarget it through a series of different configurations and see how much time it takes. In our first case, we're considering the simplest case of a daisy chain register, where the PDL code needs to be streamlined in order to access in parallel the different registers. Thanks to the MAST tool, we were able to produce a really fast retargeting, even for a high vector count, so going up to 100 register, 100 the other, making either 10 up to 1000 different accesses. We can see that the retargeting time is linear, which is optimal in this case. We then explored the case of nested SIB registers. So we added the complexity of retargeting and making the dynamic topology configuration. We can see that even though the retargeting time in absolute is slightly bigger, we can still have a completely linear progression. Lastly, we made a stress test where we're putting the two things together. So we have 100 chained register with 100 different PDLs to be retargeted, each put in a series of hierarchical levels. Once more, we can see that even going to a big register count of hierarchical levels, we're still getting completely linear cases with a minimal vector size, therefore proving that our tool is able to support these big cases and handle high-scale parallelization.